All right, so moving right along in Chapter 7 here, we've covered a couple of the named gas laws, and here we're going to combine a few of them in what's known as the combined gas law. So up to this point, we've studied Boyle's law, which relates pressure and volume, Charles' law, which relates pressure and temperature, volume and temperature for Charles' law, and then pressure and temperature for Gay-Lussac's law, and we're going to combine them all into a single combined gas law here and see that once you learn this one, you really don't need to know those individual laws. You just figure out which thing is being held constant if only one change is being made. So this should look familiar. Remember, Boyle's law was P1 V1 equals P2 V2. Charles' law, V1 over T1 equals V2 over T2. And Gay-Lussac's law, P1 over T1 equals P2 over T2. We combine those three individual laws into P1 times V1 over T1 equals P2 times V2 over T2. And now suddenly we can handle when pressure, volume, and temperature are involved, and only keeping N, the number of moles, constant. All right, so by using the combined gas law here, we can derive any of the individual gas laws that was used by just omitting whatever property doesn't change. So you see here, if we hold T constant as well as N, which has to be held constant for all cases, then we have Boyle's law. If we have P constant as well as N, then we have Charles' law. And if we hold V constant as well as N, of course, we have Gay-Lussac's law. So we use the three laws combined to get this combined gas law, and we can regenerate any of them by holding one of those properties constant as well as holding N constant, as we've done always up to this point in our chapter. Let's go ahead now and practice using the combined gas law. So in this problem, we have a 0.180 liter sample of gas, has a pressure of 0.800 atmospheres at 29 degrees Celsius. At what temperature in degrees Celsius will the gas have a volume of 90.0 milliliters and a pressure of 3.2 atmospheres? We're holding N constant, but we are making changes to both volume and pressure, and we've got some units that are going to make problems for us. If you look, the original starting unit for volume is liters, and the final unit is milliliters. And of course, temperature, we're going to have to convert out of Celsius to Kelvin, and then finally back into Celsius, because that's what the question wants the unit for temperature at the end. So a seemingly simple question that's going to take us a little time, but as long as we follow our steps, we should be fine. So step 1, organize the data in a table of initial and final conditions and analyze the problem. So condition 1, we have our initial pressure of 0.800 atmospheres, our initial volume of 0.180 liters, our initial temperature of 29 degrees Celsius, which converted to Kelvin gives 302 Kelvin. Our condition 2, our final conditions, we know that pressure 2 will be 3.20 atmospheres, volume 2 will be 90.0 milliliters, which we can convert to 0.0900 liters. Likewise, we could have converted that 0.180 liters into 180 milliliters. We just had to convert one way or the other, and here I've selected to go into liters for both. And then finally, T2 is what we're solving for, first in Kelvin and then back into Celsius. So in order to complete step 2, where we rearrange the gas law equation to solve for the unknown quantity, we're going to have to get rid of two things. In this case, we're looking ultimately for our final temperature, T2, and so in order to isolate T2, we could multiply both sides by T2 and then divide through by P1 V1 and then multiply through by T1. And that gives us, again, a fair deal of work here to get the form of the equation T2 equals P2 times V2 divided by P1 times V1, and that's all multiplied by T1. And finally, moving into step 3, where we substitute those values to solve for our unknown, we have T2 equals 3.20 atmospheres divided by 0.800 atmospheres times 0.0900 liters divided by 0.180 liters, and finally times 302 Kelvin gives us a final temperature T2 of 604 Kelvin. Of course, since the question wanted the temperature in degrees Celsius, we have to go back and convert that 604 into Celsius by subtracting 273 to get a final value of 331 degrees Celsius. So using the combined gas law gives us a little extra work, obviously, compared with using any of the individual gas laws, because we can be making changes to multiple features moving from condition 1 to condition 2, and that can get a little bit messy, although hopefully not too bad, as long as you go through it stepwise and just follow the initial and final values. All right, so let's see how you do on your own with this learning check. A gas has a volume of 675 milliliters at 35 degrees Celsius and 0.850 atmospheres of pressure. What is the volume in milliliters of the gas at minus 95 degrees Celsius and a pressure of 802 millimeters of mercury if we hold number of moles constant? So please pause the video at this point. Go ahead and do your best to solve the problem. When you're set, start us back up and we'll see how you did. All right, so hopefully you started with step 1, you organized the data into a table and analyzed the problem. Condition 1, you have P1 equals 0.850 atmospheres. V1 has a value of 675 milliliters, and T1 is 35 degrees Celsius, which when converted gives us 308 Kelvin. Conditions 2, we have pressure now in millimeters of mercury, 802 millimeters of mercury, so I preferred to convert that into atmospheres, since atmosphere is the more typical unit. You could have converted the P1 from atmospheres to millimeters of mercury. The key was just to have like units at the end, and that gives 1.06 rather atmospheres. V2, you don't know what it is, but fortunately you need it in milliliters, and since V1's in milliliters, if you do everything else right, you should end up with V2 in milliliters. T2 minus 95 degrees Celsius when converted into Kelvin gives us 178 K, and that's the one condition. The temperature conditions will always have to be in Kelvin, and then as we saw in the previous example we worked together, we needed to convert back to Celsius at the end. But in terms of pressure or volume, as long as they're the same units, it doesn't matter which unit you pick, but for temperature it does always have to be Kelvin units when you're solving these problems. Okay, so here we are into step 2. We can rearrange the gas law equation to solve for the unknown quantity. So in this case, we're actually looking for V2, and after we've done our rearrangements, we should see that V2 equals P1 times T2 over P2 times T1, all times V1, or we could have the V1 out in front, but however you rearrange it, we end up with that same overall form. And here in step 3, we'll go ahead and substitute values into the gas law equation and calculate our final value of volume here in milliliters. So V2 equals 675 milliliters, which was V1, times our 646 millimeters of mercury over 802 millimeters of mercury, times our 178 Kelvin divided by 308 Kelvin, and we end up with a final value of 314 milliliters. So there we go, a little bit of work, hopefully not too bad, and hopefully that's the final volume that you ended up with. If not, hopefully you've caught where you may have gone wrong. If you're still lost here in section 6 of chapter 7, please reach out to me and we'll do our best to get you back on track. But if things are going well, then we'll see you again for section 7.